This video is still under the heading of multiplying polynomials. However, we are going to look at special ones that we multiply. And there's three special things, actually two of them that we memorize, these two. And then the third one we'll just kind of discuss to look at how we can continue on to build on some of the patterns that we see. And so we'll look at a cubed binomial and then maybe even ones that are to the fourth power, etc. So let's focus on conjugate binomials first. So here we go. Let's look what they, or let's first write down what they look like. Conjugate binomials are ones that look like this: a plus b and a minus b. Their first term is the same. Their second term is the same, but they have opposite signs just right there in the middle of them. And so if we were to do some that have some coefficients and numbers in them, it'd be like 3x minus 4 and 3x plus 4. As long as they've got that difference in sign, here I've written the negative one first, 3x minus 4, and its conjugate binomial would be the 3x plus 4. And so they all look like this. We'd have a negative 7x plus 2y squared, and then the conjugate binomial would be 7x minus 2y squared. Again, they just differ in that sign in between the two terms. And when we multiply conjugate binomials, we're going to see something interesting happen. So we'll start with a nice, easy pair here. And I'm going to multiply that conjugate pair. And now this is a distribution problem. But what we're going to find out is that these all tend to look alike when we get done multiplying them. And so we can use some shortcuts because we already know what's going to happen. And so I've distributed my x to both the x and the negative 3, distribute my 3 to both of them. And you can see in the middle here what happens. Because these are conjugates, we get this positive 3x. And then we always get this opposite, this minus, in this case, 3x. And those two will always cancel out. And so conjugate pairs tend to only give us these two term polynomials, or they return another binomial. So let's do another one. You'll see this pattern continue. Let's say we've got 2x minus 4 times 2x plus 4, again a conjugate pair, differing only in that sign in the middle. And we get 4x squared, 2x times 2x. We get 2x times 4. We get negative 4 times 2x. And then lastly, we get negative 4 times 4. And again, we notice we get a plus and a minus here, and so those two disappear. And so again, we only end up with a binomial at the end. And if you notice here, this is the 2, and if I square 2, I do get the 4x. This is a 4, and when I square 4, I get 16. In fact, if we want to develop a general formula for for conjugate pairs, we could just say, let's say we have a polynomial a plus b and its conjugate a minus b, and let's just look at how these things multiply out to give us a general rule. So I'm just distributing like normal. I get b times a there, but I'll write that as ab. Oops, one of these should be minus. It's this one right here. Okay, that's a times negative b, so that's a negative ab. And then my last term here, I get negative b squared. And so you can see these things right here do disappear. And so the product of a conjugate pair, a plus b times a minus b, is simply take the a and square it and subtract and take the b and square it. And so we can now, once we understand that, we can perform operations with conjugate pairs very, very quickly. I don't have to go through that whole distribution process. I just want to take my a value, which is 3x. It doesn't matter which one you look at. They both have the same a. And you can either think of it as taking the 3x and squaring it, like it says to do here, or you can just think 3x times 3x. So it's just doing this multiplication. And then you go minus sign, because that's what the formula says right there. And then it says take the b value, which is 2, and square that. So that's 4. That's what the product of 3x plus 2 times 3x minus 2 is. And we're done. So if we have a conjugate pair, we can do these multiplications very, very quickly. Here's another example. Conjugate pair. I square the 5x. That's 25x squared. I put a minus sign, and I square the 1. That's what it multiplies to. We don't have to go through all the math anymore. Okay, this only works with conjugate pairs. Plus 2, and we'll do negative 6x. To be the conjugate, it'd have to be minus 2, just like that. And so if we ask to multiply those, again, negative 6x times negative 6x, and 2 times 2. And it's always minus in there. Okay, it comes from this 2 times this negative 2 right there. And so you'll always get a minus, and then it's whatever that product is. And that's how we square, or how we multiply with conjugate pairs. Next shortcut is squaring binomials. It's part of what's called expanding binomials. And here's what they look like. You have a binomial, and you want to square it. Now, a lot of students would get this wrong because they think, oh, I just square the x and square the 3. That would be true if it had been a product inside there. Then it's 3x times 3x, which is the same as 3 times 3, or 3 squared, and x times x. So when it's a product, you can do that and square each thing. When it's a sum like this, you cannot. And here's an example to prove that. Let's say I've got 3 plus 5 squared, like this. This is clearly equal to 8 squared, or 64. If you're to do what most students think you can do, which is square the 3 and square the 5, you get 34, and that is not correct. So you can't do it that way. In fact, what you have to do when it says to square something, oops, let me erase here. When it says to square something, you've got to do exactly what it means to square something. And that means to take it times itself. And so this x plus 3 quantity squared is really x plus 3 times x plus 3. Okay? It is not a conjugate pair. They're both positive signs because that's what it means. Square it, take it times itself. And so we don't get disappearance in the middle. Instead, we get something else when we distribute. Get 3x like I thought I would, but instead of getting an opposite 3x, we get another 3x. And then our last term, 3 times 3 is 9. So it's very similar in that our first term and last term are squared. However, in the middle, instead of canceling, they both end up having the same sign, and they add, or they both would be negative. We'll see that in a second. And it comes like that, or it becomes x squared plus 6x plus 9. This doubling up in the middle always happens. Let's look at a few more of these things so you can see this in action. Say I've got x plus 4, and I want to square it. Again, that means to take it times itself. And I'm just going to go through all these distributions here. X squared, 4x. And again, I get that 4x twice, and then a plus 16. So again, I've doubled up right there in the middle. And now if we relate that to the original problem here, we can see that my a here, the x, that came out first. It's just the a value squared. And the 4 here, when it gets squared, it gives me the last term. The question is, when we are squaring something, where's that middle term come from? And you can start to see it's always twice whatever that product is. X times 4 is 4x, and you end up with 2 of those, and so you end up with an 8x in the middle. Again, we can develop a formula for this. We had to get 2 4s in here, or it's 4 times 2, which is 8. And so we could apply then to all binomials that are squared. So I'm just going to square this thing by hand, and then we'll see what the results should always look like. A squared, a times b. B times a, which is the same as a times b, and then b squared. So we get a squared and b squared, but in the middle, you get ab plus ab, which is 2 of those. Remember on those other, use that multiplier by 2 to get 2 of those middle terms. Now watch the way this works. So now that I have a general formula, I can write any binomial I want, and I can square it. How do I square it? It says take the a value and square it. It says take ab, multiply them, so 4 times x, that's a times b right here, and double it, because you got to take it times 2, so that's 8x. It says take your b term, and square it. And there we go. I've just done x plus 4 squared without having to do all that distribution. A few more examples so you can see this in action again. I kind of have to talk you through this because when you're doing the shortcut method, there's not a whole lot to write down. Okay, I need a squared first, so my a is my first term there, so it's x squared. Then I need 2 times the product of a, b. So a is x, b is 6, so it's 6x, but then I have to double it. And then my last term is always b squared, so just 6 squared. And then finally, kind of a tough one here. Let's make this 4x squared y. Actually, let's make that 5, just so we don't confuse it with another 4 that's going to pop up. Minus 6. And I want to square that binomial. So here is my a value. And I've got to square that. And all that means is to take it times itself. Okay? And this is super easy to do because all you got to do is the 5 by 5. And then be careful, x squared times x squared, x to the 4th, and y times y. So there's your a squared right there. All you do is square the 5, square the x squared, square the y. Then we've got to multiply these two together. Now when you multiply those two, really just focus on the numbers. Negative 6 times 5, that's negative 30, and you double it. But we also have some variables here in these products. Remember, it wasn't just negative 6 times 5, it's also times an x squared y. And so those have to be thrown in here as well. That's the full product. 5 times negative 6 with the variables, then you double it. So that's my plus my 2ab. I know it's a minus sign, but it's a minus sign because of that negative 6 there, giving us the negative 30 that we doubled. And then lastly, you just have to take b and square it. Well, b is this negative 6 right here. And negative 6 times negative 6 is 36. Now, one more time without all the talking, so you can see how easy this is to do. And then let me write these above it here, so a squared. Just following this model here, a squared plus 2ab. And that's what a plus b squared is equal to. Oops, forgot a b in there. So we go, a is this. My b is right there, and we're going to take the sign with it. And we just go a squared, that's 49x squared. We multiply, that's negative 14xy, so negative 28xy, because we have to double. And then negative 2y times negative 2y. And you're done. That's my b squared, that's my 2ab right there in the middle, and there's my a squared. Now, if we start to continue this, that was an expansion of a plus b quantity squared. We can do this further, okay? We could do it with something like a plus b cubed, and we can write general formulas for that. In fact, to develop a formula for that, we'll go ahead and do it here real quick. That's the same thing as ab times a plus b squared. It's still ab times ab, but this 2 means, and think about it, it's just having a 1. That gives me a total of 3 of them multiplied together. There's one of them, this is 2 of them. And I wrote it this way on purpose, even though it's still a plus b cubed, because we just looked at the shortcut for expanding a binomial. So I'm going to write down the expansion of a plus b squared. We just saw it. It's a squared plus 2ab plus b squared. And then to finish my multiplication, I just have to distribute the a to 3 terms. A cubed plus 2a squared b plus ab squared. And then distribute the b, giving me ba squared, which I'm going to write as a squared b, giving me 2ab squared, and then lastly giving me b cubed. And I've lined these up a little bit so that my like terms were the same, or lined up, I should say. And that's what we get. So this would be a general formula for something cubed. Now, it gets really long here, obviously, to try and memorize a formula like this. But it's not all bad news, okay? There's some certain things that we can look for in this pattern. The first thing is, notice this was a cubed thing, so we start with an a cubed, and we also ended with a b cubed out here. So we know the beginning and the end of it. We just didn't know what other variables came in the middle, but look at what your a does. Your a started a cubed, then it went to a squared, then it went to a to the first, then it went to no a's. Your b's, on the other hand, did what's called ascending order. B to the 0, it's not even shown in the first term, b to the first, b to the second, b to the third. So even if I didn't know all these numbers in front, in this case those 2 3s, I knew what my a's did. In fact, if I were given an a to the 4th problem, I could legit write down at least the variables. It would start with a to the 4th, and it's going to end with b to the 4th down there. And then my a's, remember, just go decreasing order like this. Oops, make that a squared. A and no a's. And my b's do the opposite. They start with no b's, then b to the first, b to the second, b to the third, and then there's that b to the 4th that it ended with. So I actually know what each term looks like in regards to its variables. The a is going downhill, the b ends up going uphill. That's because the a came first, so it gets a to the 4th at the beginning, going down to no a's, and the b gets it at the very end. Okay, now it's just these coefficients, the numbers in front, that we have to figure out. And those turn out not to be too bad. In fact, I can write down what they are here. This would be a 1, a 4, a 6, a 4, and a 1. And so if we understand how to write these variables, then all we have to know how to do is where to get these numbers from. Now to get these numbers, what I'm going to do is I'm going to look at the patterns that develop. And to do that, I'm going to look at binomials, and I'll start with a plus b again. And I'm just going to keep raising them to powers like this. And I'll look at what the expansion looks like when I multiply it all out. And so, for example, this a plus b squared, I already know that goes to a squared plus 2ab plus b squared. And so our coefficients would be a 1, the 2, and the 1. Remember, I know how my variables go. A squared, a to the first, no a's, no b's, b to the first, b squared. A is descending order, while b is ascending order, going uphill. Now, a plus b to the first power is just a plus b. And so the coefficients there are just a 1 and a 1. And anything to the 0 power, like in a plus b to the 0, is just 1. Some base to the 0 power always gives you 1. For example, 3x to the 0 is just 1. A plus b to the 0 power is just 1. And so I can start to see this pattern going here a little bit, and we may or may not recognize that, but it looks like this. I've got 1, then 1, 1, then 1, 2, 1. And this is the beginning of what is called Pascal's triangle. Very easy to build this thing just from memory. because you'll notice it just has ones on the outside of this triangle. This line right here, the 1, 2, 1, this is where that 2 comes from. When you're building Pascal's triangle, the next line you kind of put the numbers in terms of gaps, and whenever you have a gap, you add those two numbers together to see what fills it in. So my next line, this would be for a plus b to the third power. Building on Pascal's triangle, 1 on the outside, here's a gap, and 1. So if I know those coefficients, I can write the expansion of a plus b cubed very quickly, because it's going to go, remember, a cubed, a squared, a to the first, no a's. The b's do the opposite. They go b cubed, then b squared, then b to the first, and no b's. And now I've got my coefficients. They come right from this list right here. It's 1 plus 3 plus 3 plus 1. And we'll go ahead and do a plus b to the fourth. And now these again are called binomial expansions. I'm going to run over to my Pascal's triangle here. I'm going to have to give myself a little more room. So I got room to expand this thing. See if we can get it reorganized here. There we go. Missing a 1 somewhere. We'll put him right back there where he belongs. Okay, so I'm going to generate my next line of Pascal's triangle. It's again a 1 on the outside. There's a gap, there's a gap, there's a gap, and then a 1 on the other side. And so here I go writing a plus b to the fifth. I go 1, and there'll be a to the fourth, and no b's. My next coefficient is 4. My a goes down by 1. My b goes up by 1. My next coefficient, so I'm just running through these coefficients, is 6, and it would be a squared because it's going down, and b goes up. Then I do the 4 here, so another 4, that's a to the first b cubed, and my last term just has a 1 in front of it, and it's b to the fourth. And I'm going to expand this triangle again. Again, I'm going to show you how quick you can generate it. So if I want to do, for example, a plus b to the fifth, okay, what I generally do is say, okay, I go into the fifth power, I'm going to find my coefficients. And so I quickly generate, filling in gaps, Pascal's triangle. Here's my 5, a 10, a 10, another 5, and a 1. There's my line I want. And so I can now write my polynomial. It's going to be 1a to the fifth. That's my first coefficient. Plus 5. The a goes down. The b starts to appear. Then comes a 10. A cubed b squared. Then comes another 10. A squared b cubed. Notice these exponents here always add up to 5. 2 plus 3. 3 plus 2. 4 plus 1. Just a 5. Because when it's a plus b to the fifth, that's what your degree is, and the degree of every term. So I've done my 1, 5, 10, 10. I'm ready for this next 5, so it'd be plus another 5, but now it's a to the first, b to the fourth, and my last coefficient is 1, and it's b to the fifth. So that's how we expand them, using Pascal's triangle, trying to shorten up some of these problems. Now, unfortunately, it's not always that easy, and let me show you what I mean by that. Let's do a cubic binomial. So let's say I've got 2x plus 3, and I want to cube it. If I'm going to do this problem, I don't have just a and b like I had in those examples. My a now is a 2x, and my b is a 3. So there's my a, and there's my b. And I know my coefficients for cubes. It's 1, 3, 3, 1. And so I can just write those down. 1, 3, 3, 1. And I can figure out each term now. So the first term is 2x, that's my a, and my a is to the third power. Then my a is to the second power. Then my a is to the first power, and then my a is to the 0 power. I'll show it this time. That's just 1 again. My b now is a 3. So it starts with no 3s, 3 to the 0, then it has a 3 to the first. It's the b going in ascending order. You can see it ends up with b cubed. And now all you have to do is evaluate each of these little expressions. Like 3 to the 0 is just 1. So it's 1 times 1 here. We just got to figure out what 2x cubed is. So 2 times 2 is 4, times 2 is 8. So this is an 8, an 8x, and it's cubed. My next term, see what we've got here. We've got a 2 squared, that's a 4. This is going to be an x squared term. You can see the x being squared right there. So we got a 3 times a 2 times 2, so you have to square it. So that's 3 times 4 times 3. I'm going to think of that as 9 times 4. 3 times 3 is 9. 2 squared is 4. So 9 times 4 is 36, and that's my x squareds. Next, I've got a 3 times a 2 to the first, which is 2, times a 3 squared, so that's a 9 times a 2 times a 3, or 6 times 9. 54, and I've got an x to the first in there. You can see the x to the first right there. Then my last term, I've got 2x to the 0, so that's 1 times 1, and 3 cubed is 27. And there, I've just done that entire expansion. And now, were I asked to do this, and I couldn't remember the expansion, look at what you'd have to do. When I square 2x plus 3, that really means to multiply it 3 times. And so I'd have to carry out all this multiplication to get to this same result. And I'm going to go ahead and do that so you can see it. Now when I do this multiplication, what I'm going to do is I'm going to group those two and do that second pair first. And I'm going to think of that as 2x plus 3 squared. I could have done it with the first two, group those two. But I'm going to do it with the second two. So it looks like the example I've done previously. Now the nice thing is, this one right here, this is a shortcut. We know how to square binomials now. Remember the formula for squaring is a squared plus 2ab. And so this is a squared. I multiply 6x and double it. Now I square the b. And now all I have to do is this final multiplication, which is distributing. It's 8x cubed. Notice that was in my answer up there. Plus 24x squared plus 18x. And then I would multiply or distribute the 3. And I'm going to line that up with my squared term here. That's 12x squared plus 36x, line it up under my x term, plus 27. Now combine all my like terms, x cubed plus 36x squared plus 54x plus 27. So there it all is, and you can see it matches what I had up there exactly. That's because I did a shortcut method, but get to the same result. And that's it. Now, these binomial expansion here, stuff right here is pretty darn tough, but something to keep in mind in particular, at least at minimum, keep in mind that a plus b cubed and a plus b to the fourth, even this a plus b squared, those mean how many times to write a plus b as a factor. Here's a plus b cubed, and multiply it all out.